Mode.
Good afternoon. My name is Lance French. I'm the Business Development Manager for W&M Environmental, a division of Braun Intertech, and I would like to welcome you to our webinar on soil and groundwater technology selection. Our expert for today is W&M's David McAlister. David, thanks for joining us today.
Thanks, Lance.
Before we get started, I just wanted to go over a few housekeeping items. If you have any questions, please send them through your chat tab on your GoToWebinar window. If we don't get to your questions, I will make sure that Lori and Victor sees them and we will get an answer to you as soon as possible. We are recording this webinar and it'll be available to rewatch on our website soon along with the slides. So let me introduce you to David. So David is a Project Manager 3 with W&M Environmental, a division of Braun Intertech. He has a BS in Environmental Science from Stephen F. Austin. And I just want to say thank you. You might be one of the very few people who have actually hosted a webinar that did not graduate from Texas A&M. So thank you for that. They're few and far between. And he has 16 years experience with soil and groundwater projects, almost exclusively. So
right.
You've been in the business for quite a while. Mm-hmm. So, well, we appreciate you coming. This is actually your second webinar that we've had you on. So, yeah, last year you did one on wastewater.
Yep.
And yeah, you were here for like about a month, and then we threw you in and said, hey, try the water. It's great.
It's pretty quick.
So, so if you haven't seen that webinar, you should go to our website and type in wastewater in the search bar, and it's a great information on wastewater. So, okay, so David, let's get started. Let's go over the big picture here. So, what are we talking about today?
Sure. So we're looking at sites that are headed towards remediation. We want to talk about what the approach is to find the right technology to clean the site up. So, in looking at the big picture, we know we've got a problem.
So this is after the phase 2, or you already kind of know what
industrial site.
Yeah.
You've got evidence or reason to believe there's an issue. So we know we've got some kind of problem. So we need to find out how much of a problem we have. We need to know what cleanup looks like. What are our levels, and then we can start to look for solutions that fit. Out of all the range of solutions, we're going to start to filter out things based on these boundary conditions on time scale and some other things, and then we'll select the best one and get after it.
Okay, so when you said success, so here we are. What does success look like? So when you come back to your office, you're putting together a strategy. So
right,
take me through that.
Yeah, it's time scale, cleanup level, and budget. Right. So it's how long is this thing going to take? And it's not necessarily from the remediation end, but from a regulatory or client-driven end. A lot of that's going to be one of your boundary conditions really frequently. The client needs to redevelop the property. Regulators need this done by X date. Those are one of the conditions we want to set up front and see if we can meet or exceed. And then the cleanup level, saying what program is this site falling into? What classification is the groundwater? How clean do we need to get it to establish closure? And then what's the budget?
That's the money.
Yeah. So in at this point, in kind of setting the boundaries, that's an order of magnitude cost. Is this a private party that's got 500 to spend and you're going to go out there with a shovel and get a little surface soil, or is this a huge site that nothing's going to touch it for less than multi-millions?
So 2 of those 3 are basically client-driven, really.
Client
pretty much, yeah. Okay. So the developing your conceptual site model.
So the second part to the kind of the early scoping approach and figuring out what we're going to do to fix this place is we've got our boundary conditions, and now we need to know what the site's doing, how it's behaving. So we want to plan on spending a little more time and money than you think you should on the front end, especially for a complex or complicated site, to get really good data to really understand what's moving where and how it looks. We want to gather that data up and integrate it to get the best types of visualizations to really understand. And the primary reason for doing that is the more good data that we get, the more precise we can be with our remediation, And then a second thing is you might discover some other stuff going on there that you were unaware of.
Okay. So we're looking at this model right there. I don't know if the audience can see that. We're looking at the picture right there, the 3D scale. So how do you get a picture that accurate?
Yeah, so it's going to be the number.
Pretty impressive.
It's going to be the number of data points and the type of data collection. So something like that could be achieved pretty well through some of these direct push high resolution site characterization tools. It could be done with high density soil analysis. It's a little tougher to do that. This was actually probably set up that way on a couple of transects. So they're looking at contamination both vertically and then along the transect, and they're kind of piecing the map together from the information coming back. But that's the idea, is to get enough data points in there that you can see where it is and where it's not, so you can focus your efforts. Make sure you're hitting all the areas and focusing the efforts.
So the alternative to having something that high speed, so you're talking about bringing some technology out to the site, and they basically is it kind of like a rover, or how does that work?
There's usually a geoprobe tethered to a van with a whole bunch of equipment in it.
That's kind of cool. Yeah.
And
okay, so then what are the alternative to that is probably what, soil.
Lots of soil samples,
soil
generally,
and stuff. Okay, so what's the pros and cons to? I mean, I would imagine that the soil borings it's going to add more time.
The soil borings will be more time, quite a bit lower on the day rate cost, with a little bit less production.
Okay.
The biggest con is that the soil samples generally need to go off-site for laboratory analysis, and you've got a pretty good delay. You can bring a mobile lab on maybe for groundwater, but you still are going to have a lag, right?
Mm-hmm.
So the ideal thing to do on a lot of these bigger, more complex sites is to collect a couple soil samples co-located with your high-res site points. And so you've got some kind of point of correlation, but then use the high-res to get real-time feedback. So you're seeing what's going on a display.
Yeah, so I would imagine real-time probably costs more initially.
It does.
But time-wise, it's probably
on a lot of sites. Yeah, you can basically chase the plume. You'll see when you're out of it, and then you can come back and go a different direction, see if you're back into it, and just continue to chase it till you've got your contamination really well delineated.
So depending on how, I mean, that would go back to the quality of time when you're strategizing, saying,
right.
hey, this is going to take 2 more weeks. It probably not. You probably get it faster, but you add another 2 weeks, or we can do it immediately, but it's going to cost X amount of dollars more.
That's right.
So, okay. Very cool. All right. Sorry, I'm getting...
No problem.
Okay.
So you can take all that data from the HRSC high-res stuff or from soil samples, and you want to be able to model where your contamination's at from a profile view for a cross-section and from plan view. So we know the aerial extent of what it looks like, and we know multiple points, lots of multiple points, what the vertical extent is. That can be done in 2D representations, but whenever possible, it's really helpful to get a 3D rendering, so you can kind of rotate it around, see if anything jumps out at you as being odd. So when budgets allow, especially on a complex site where it may go into some real big money to clean up, let's get the best information we can up front.
Yeah, that's pretty cool.
I think we touched on that next bullet on the prior slide. So there's some things that you might want to consider while you're out there as well, that I'm certainly looking at when we're even really before we're jumping into what we think might work. If we're out there doing some soil and groundwater analysis for other stuff, if we're already doing that, let's grab an extra $40 sample or whatever it is for soil oxidant demand, just in case we might go towards in situ chemical oxidation event. Even if it's a 10-15% chance that we'll go that route or this early in the game, let's go ahead and grab it. We're already out there, save the mobilization cost. Same thing for dissolved iron or hardness. If it might swing towards a pump and treat system or a DPE system, if there's a whole lot of dissolved iron or really high hardness levels in the water, you're going to want to know that up front, because that's additional cost for operations and maintenance, and maybe some additional capital cost. That if you didn't know that, you put the system in, now you've got all this inorganic fouling messing everything up, and now you've got a retrofit, and you weren't planning on the cost for the chemical and the other stuff. So just a few upfront considerations.
Okay. Hey, I know that man.
Send the A-team, right?
Send the A-team. So I was, when I saw that earlier, I was like, I pity the fool that doesn't log your borings right.
So I guess the point here is we really want to see a high level of detail in soil boring logs that are going to be interpreted for remediation planning. Send some senior folks out there, and try to send the same folks every time, so there's a whole lot of consistency in what's being put on the logs. I think a lot of us out there have seen 50 pages out of 100 where it just said clay, same as above, page after page with different boring log numbers. That doesn't mean that's inaccurate, but they may have missed some subtle variations in color or sand content or silt content. So we want to make sure we can really count on the data that we're getting, and double check historical data that we're using. If we're out there for another reason, can we get the A-team geologist or geoscientist out there and see how one of the logs that they worked compares to some of the older stuff, and use that to kind of QC some of the other things that you're leaning on.
So have you ever been out to a site where the logs were so bad you just basically, at that point you just start over, or do you
I've seen some pretty rough ones, out there.
Yeah, we can't use any of these, so we just have to start from scratch basically.
We've definitely gone out and done some confirmation borings to see how much they compared, and a few of them were questionable enough that we swayed our decision making away from using that data in the larger picture. We didn't have to recollect all of them, but we definitely got enough to make good decisions.
Okay.
That goes into variability in lithology. So what's your soil profile look like vertically, and then from area to area on the site? Because the more variation there is in soil types on a given site, the more complexity you're picking up, and generally that complexity it can lead towards dramatically increased cost. So the modeling on the front end, the really understanding, having a good conceptual site model, helps offset some of that additional cost by being able to focus our remediation efforts on specific areas instead of applying site-wide. You may have on half the site, it might be 10 foot higher where we need to address than it is on the other half, and the same goes for concentration gradients. And there's a lot of considerations that go into it that really make you want to pay sharp attention to all the details. So before we get into, or as we're getting into the preliminary screening, or taking a look at what possible technologies we're going to use, we want to make sure that conceptual site model is locked down, understand that budget, and understand those end goals. So once again, we're going to come back and we'll look at those and go, okay, let's put together the long list that's cut down from everything with things that look like they might fit into there, and then we'll look at the other site conditions on top of that. And there's the site-specific conditions as well come into play that are part of the conceptual site model, but also maybe some external conditions like off-site access, or what utilities are running through there, and what bearing those utilities, subgrade utilities or overhead utilities, might have on how we go about doing things.
Okay. So do you have any examples of where you had to combine technologies to hit the end goal?
Yeah. One jumps out. We had a gasoline tanker rollover in Oklahoma.
Yikes.
Yeah, it was a good one. It fully emptied at the top of a hill and ran a bunch of different directions.
Whoa.
So of course, they did the emergency response work, which included some limited excavation, but the soil was as such that it got in and got to groundwater really fast in quite a few places. So once the excavations were backfilled and confirmation samples were taken, we noted there was a few different areas that had either really elevated dissolved phase levels or some limited LNAPL or gasoline floating on the groundwater and absorbed into soil. So the approach we took there, we started off with a dual phase extraction. And this was a mobile application, so we did a couple 7 consecutive day events running 24 hours a day, and we're able to get the mobile LNAPL down to pretty much a sheen, if not gone completely in a few limited areas of the site. We knew that wouldn't make our dissolved phase standards, so we followed that with a persulfate-based injection, which is a chemical oxidizer that breaks up the contamination into CO2 and some innocuous gases. But we also knew that we couldn't over apply the persulfate in that area based on some nearby utilities. So after 2 rounds of persulfate injection, we took a step back and waited for it to play out its course of activity. Did some confirmation sample, found an even smaller area that needed some additional work, and had planned on it before. So we did an oxygen release substance as a slurry in those limited areas that stimulated the aerobic biological growth to chew the rest of it up and got the site to closure.
Very cool. So
3 different technologies.
So when you're going to a site, if that can happen. So basically, on a very simple term, it's like going to the dentist, and he's not just going to do a root canal if you have a cavity. He's going to probably just give it a filling first.
Right.
Right. So okay. So I don't know if that was a good example or not.
No, that works. That works.
You make me feel like I should have paid more attention in science class. I'll tell you that right now. So okay.
All right. So then we get into screening.
Woo!
Yeah.
All right. Yeah. Uncross your eyes. Let's go. So what are we looking at here?
Yeah. This is kind of what a lot of practitioners are doing in their head, kind of on paper. This matrix was set up for a gasoline range LNAPL site, graded under site specific conditions. But what we did on the left side here, under technologies, we looked at pretty much all the available technologies that would be somewhat reasonably applicable to this type of release on this type of site. And then we went through and started kind of categorizing them by their characteristics, their strengths, and their weaknesses to try to get a big number on the right side of the page that is leading towards higher applicability for the site. And we really want to make sure we're not leaving any options off the table at this stage, because if we didn't put it on the list and we didn't look at it, it might have been an option.
So, but I would imagine if you give this to your client, he's going to look over here and say, $51 million. Well, we're not going to do that one. We're not going to do the $30 million ones. I like these up here maybe a little bit better. So this is basically, this is the method. This is the cost. Is there a time?
Yeah, there's a relative speed of application is one of the first ones. And there's a few different ways, and the weighting system on this and the tech score is also it's pretty subjective, but it's also weighted towards site specific conditions. So what are those big picture goals? So that's what we're going to.
And this is just for a Giro LNAPL site. So
if this was any site, that list would be a whole lot longer. There's a lot of different technologies out there. So
I'm probably going off, but is there things that you might say, hey, we're going to use 2 of these?
Yeah. So one of the columns on here, that's one of the things I want to look at is on here it's listed as AOC wide, or area concern wide. So does that mean this technology would be good for all of the site for all of the problem?
Okay.
Or does a site need to be divided into multiple areas of concern or multiple treatment areas that need to be addressed with different technologies. So we're trying to address that in there as well.
Okay. So it just looks intimidating. It's not that intimidating when you look at it.
No,
when
no.
you first look at it, you're like,
yeah.
what?
Yeah, but
all right.
Just go through and consider
So
how that thing works
one?
versus what you got to work with. All right. So we get into
pilot testing.
Yeah.
So that sounds like to me when I hear pilot testing, that it sounds experimental.
Oh, that's kind of the point. It certainly is. So once we've gotten through that screening checklist and we've identified a couple likely candidates, we'll end up engaging the stakeholders. So everybody that's got some skin in the game, from the field techs that are liable to be out there, from the folks who've been on site up to the client and regulators. Everybody's going to have some opinions that need to be considered, and that's a great opportunity to maybe find some boundary conditions that you hadn't thought of, that might push towards one technology over another. So make sure we're having those meetings briefly but frequently with lots of folks. But at the end of the day, we'll probably come down to one favorite that looks like it's going to meet most of the best criteria. So we'll design a pilot and just basically a tiny scale version of what we intend to do full scale site-wide, right? So we'll go out and see if all of our work on paper lines up with what the site's willing to let us do, right?
So have you gone out and figured out? Have you been out to a site before and you had one technology or one procedure that they think is going to work, and nope, you knew right away, or maybe after a while, hey, this one's not the best way to go about it.
So I've been a part of a ridiculous number of full scale site remediation projects. I can tell you I've been a part of more than that number for a pilot test, right? Okay. And that gap is that gap is you want to do a pilot, you're wise to do a pilot before you do a full scale. The pilots don't always work, so then the full scale, at least that way, doesn't always happen. So
and ultimately that's, it's a value to your client, doing it, because you don't want to do a full scale remediation then find out that one didn't work, and then and then so there's somebody's going to get the bill for that.
Right.
It probably isn't going to.
So on a pilot, there's kind of two ways to approach that. Also, if there's a lot of apprehension on whether the technology will work, you might not do a full-blown performance test, and you might do a limited feasibility test. Especially with injection, it's hard to predict how well a site will accept fluid or slurry at reasonable production rates. So it may be that you do a very limited, 1 or 2 point. Will this take, and at what rate, and then come back with a performance test or a treatability test. Both of those, a lot of times you're getting both the feasibility and the performance in the pilot scale. So a lot of folks will do a 3 to 5 point pilot within a certain distance of one well. But it's
very cool. Yes, it's cool. I think it's cool.
Thanks. Sometimes it's fun.
Yeah.
All right.
Okay, so those are some interesting pictures there.
Yeah, that's a project that we're completing right now. You see an open trench there on the right with a long pipe at the end of a half-mile worth of interconnected piping that's connected to a sparge well. So basically the long pipe's going to be pushing air into a well that's screened below the contamination in the groundwater, and that air is going to evolve out of that well and spread up through the contaminated groundwater, and a lot like setting a tray of gasoline out on a hot sunny day and watch it evaporate. That air coming through there is going to volatilize or strip out the contamination from the soil. And what's not pictured here just off site from that well is a series of soil vapor extraction wells that are set above the groundwater contamination, slightly in it, that'll use vacuum to pull nearby soil vapor out plus the stripped air from this and send it off to treatment. So it's this is a pretty amazing site that's got a huge gallery of both air sparge and SVE wells, and it was a great candidate and a great technology selection for the site's needs.
So yeah, so I'm going to say that's pretty cool, and that's a half mile, is that half or a quarter?
Yeah,
half a mile piping.
Yeah.
So that means
a lot of wells,
and in that, so that's a lot of property that's contaminated.
Yeah, it's a lot.
Wow. All right. Well, I'm glad we have smart people like you to take care of some of this stuff. That's for sure. All right. There's a lot of words and a lot of bullets. So
yeah, we're not gonna go one by one and talk in detail about each. But so you've got your pilot test done. You've either found that you needed to supplement or augment or modify from the pilot test, or it was good to fully scale out. So you come to the point of implementation. Implementation starts once you've decided what you're going to do and doesn't end till the project's done. So I've just put some of the differences between doing a field event where you'd have a lot of folks out moving equipment, doing this or that, versus a system installation where you get it installed and then the system's working 24/7 or on whatever time basis that it's designed to, and then you're coming by weekly, bi-weekly, whatever it is, to take care of the thing and make sure it's all doing its job. So you see a lot of commonalities between the two. The planning to get the event going, the permitting, utility clearance, all that stuff is real common. But I did star one thing on here. I probably could have starred subcontractor selection on the other side and added that. It's kind of in the same vein. I've seen and been around a lot of systems that were underperforming for a few different reasons. Some of it correctable, some of it they missed a boundary condition and probably should have added some more wells or augmented with a little bit different technology. But one of the most common things that I see in underperforming remediation is the level of training and experience that goes in to the operations and maintenance. I think we focus really hard on providing a lot of real world training to our folks to kind of limit or eliminate any fail points related to that, to the extent that the equipment can handle. And then, once our folks learn, then they can really push forward and make recommendations for system augmentations to increase reliability and really start driving towards expedited site closure.
Okay. Oh, the pictures,
Yay,
my favorite.
Pictures. So on the bottom right is references back to that other illustration from Clue In. So we looked at how the conceptual site model might come together and might look for a site, and this is the bottom right is just an example of how you might focus your remediation efforts on where the problem is, and one design solution that looks pretty good here to address that problem. To the left of that was a mixed phase remediation project where there was injection, pump and treat, and excavation all going on concurrently at the same site. And that was a hex chrome site. That was a lot of fun.
Hexachrome.
Yeah, lots of subcontractors. It was a pretty good deal there. And then up top, both of those photos are from the same place. The left is the building, the right is the inside. That's a dual phase extraction system I designed with a great team, where we kind of had free reign to take a look at the site, develop how we thought it was going, and design the equipment, select the system integrator, and install and operate it.
So the top two are the same?
They are. That's the right one is a view from inside the
and
bay
all
door.
That is to remediate soil and groundwater.
Yeah. Yep. That was a dual phase system with a air stripper, twin rotary claw blowers, full water treatment, and I think that was a 500 CFM thermal oxidizer. So the neat thing about this site, well, it was a PST site under TERP and private insurance funding. The budget was moderate and doable. The timeline was pretty flexible, but they really wanted active remediation done in 3 years and rebound monitoring, the following 2 years. So five-year time frame, including rebound monitoring. So we designed the system, and then about the same time, it's not new now, but a brand new patent came out for a brand new product. That's a downhole product on the end of your drop tubes, which are like big straws that suck out groundwater, soil vapor, and the floating LNAPL. Well, they're generally fixed, and this product floats right at the surface of the LNAPL and will follow it down. If you have groundwater rebound or some kind of influx, it follows it back up, so it limits the amount of groundwater produced. That was a big benefit to us because on this site, we knew ahead of time going into it from some geochemical analysis that the site's dissolved iron was ridiculously high. So we knew the more water we had coming through the system, the more scaling we were going to have, and the more money we'd have to spend on scale control agents. So using this product increased our vapor, which also means we decreased the amount of fuel gas we needed on the thermal oxidizer and decreased the amount of liquid LNAPL coming off the oil water separator and ultimately going to recycle. So it was a great deal, and what it ended up doing was cleaning the site up in 18 months.
Wow.
There was a neighboring PST site that had been operating for about 7 years with some kind of undersized equipment that was in pretty substantial disrepair, and they were maybe 50% done. Well, our radius of influence for our groundwater and soil vacuum kind of trimmed in ways into their site, so we ended up cleaning up a few of the wells on their side.
Wow.
Inadvertently, but we had to get ours done. So, and it made it through its 2-year rebound monitoring with no problem. So
probably room to spare too then.
Yeah.
Wow.
So
that's pretty cool. Was that one of your favorite projects?
It's one of my favorites with that type of equipment. Yeah.
So I'm gonna put you on the spot here. What's one of your most unique or favorite projects that you've had to work with, and maybe there's a tricky twist to it that we had to put the famous David McAlister brain to it?
So EHC is a product with zero valent iron and a ground up plant matter carbon source. It's really good for chlorinated sites, but a lot of times there's not enough Helicoides bacteria present in the soil. So if the zero valent iron doesn't fully reductively dechlorinate your COCs through the abiotic pathway, then if you don't have that bacteria, you'll stall at the daughter products or vinyl chloride. So you've got to go back and add the Helicoides bacteria after the geochemical of the site kind of get where they need to be for those bacteria to be happy. So we had a client challenge us to figure out how we could do the two concurrently. So we got the opportunity to start mixing our EHC slurry with water that was already anaerobic. So start working in South Texas and making multiple 1,000-gallon batches of anaerobic water that you're keeping day to day. We're prepping tomorrow's the next day, and there's always a little bit left over, so it gets pretty stinky and pretty funky.
Wow.
But you buffer it for pH, you mix that, and you use your anaerobic water as a carrier to inject your bacteria at multiple points in the wells, and it was fun coming up with that process and working out the client's needs and getting it done successfily.
So you know how I knew that's a cool job?
How's that?
Because I didn't understand any of it. So that's
well, remember Stinky.
I did know Stinky. So hey, what we were talking earlier about, there was another project that you were talking about, one of the Air Force projects. Do you remember that offhand?
Yeah. I think we were discussing how. So we talked a little bit about how you might use multiple technologies as a phased approach. But co-applied technologies can sometimes open up some otherwise closed doors. Some people call them combined remedies, a few different terminologies out there, but the concept's the same. We know we need to do this with this, but we can't because of that. So the co-applied concept is where how we can look at potentially getting over some of that. So the Air Force site had a pretty plastic clay, and they had some low-level chlorinated solvent issues that were kind of lingering, and it was the only thing holding them up from closing this whole unit out. So they looked at injection, but the shallowness nature of the site, shallow groundwater, and plastic clays meant you were going to struggle to get 1 gallon a minute of injection at like 100 psi. And your radius influence, or your reach from the injection point away from that point into the formation, was really limited. So you would have needed an astronomical number of points with really low flow, which means really low time, or really long time. So the Air Force was willing to try something a little bit different, and we went in hollow stem augered, or actually solid stem augered on that side, some 5 and 6 inch holes, and pneumatically fractured with liquid nitrogen to open the formation up. It sounds like a shotgun going off, even though it's 12 foot down. You kind of feel a little rumble in your feet, and pow! It's pretty cool. So
it is pretty cool.
So it opened up. It opened up the formation through a series of fractures at multiple levels in each boring, to the point that we were able to inject 75 plus gallons a minute of the remedial amendment for volumes of up to 400 and 500 gallons per point. So we're you
went from 1 gallon to 75 gallons
per minute as rate.
Wow.
And from maybe 15, 20 gallons of total fluid acceptance before surfacing, up to 400 or 500 without any surfacing. So got our full volumes in, and the last report that site was heading towards closure.
Has there been anything that you've come across you're like, yeah, I can't do this one. This is something that can't be done?
I haven't come across anything that can't be done yet. It's that you can't afford to do what the best option is.
Gotcha.
I'm still looking to figure out a great thing for a creosote site. So I've been after that for a decade now, and hadn't got that cost down.
And that big spreadsheet that we showed earlier. Yeah. Have you had anyone that has ever done the $50 million projects?
I haven't been a direct part of it, but I've been adjacent to some very large thermal projects where thousands and thousands of amps worth of high voltage power were fed to electroresistive heaters that were placed into the ground to cook the soil to a couple hundred degrees and bake all the water and contamination directly out of the ground, to the point that the down gradient monitor well temperature a year later was over 150 degrees Fahrenheit.
Wow.
So,
that's crazy.
Sometimes it's the right answer.
I've been watching that show that series on HBO called Chernobyl. That is just fascinating. I mean, it's not anywhere, but that's just similar things, because it was a nuclear reactor that was melting.
Sure.
But the biggest concern really was contaminating the groundwater, and it was going to go into one of the rivers. It was not just going to contaminate Russia; it was going to contaminate like entire Western Europe or something like that. Eastern Europe, I guess, would be so, or Western. I don't know. Yeah, whatever. I guess I don't know geography. So. All right. Well, any other examples you want to, or is that pretty much it?
I think that's got it.
All right. Well, thank you for that very informative webinar, and I'm sure that if we were actually live, we would actually have some questions from our audience, but because we had technical difficulties, it was just a little bit difficult for that, and after a couple of tries, we got it fixed. But if you have any questions on any contaminated soil or groundwater, and you want to get in contact with David, here's his contact information, email address, phone number, and LinkedIn as well. So, David, we really appreciate you coming in and doing this. We know that they're not always the most favorite thing to do, because they're nerve-wracking, especially when you have technical difficulties, and it can get tough. But I just want to bring up our next webinar next month on June 27th. We're having a fire stopping webinar with Eric Bergman, and he's going to explain the process and how to protect your buildings from spreading of a fire and protecting your employees and coworkers from the dangers of spreading smoke. And so it's going to be a great webinar. We're looking forward to that. So, all right, David, you're off the hook. Have a great day, and thank you for everybody who's joining in. And we will see you next time. Have a great one.
Thanks, Lance.